right? Okay, we have three people now. So we are going to have a revision of what we did last time. I'm going to revise what we learned last time. I hope you should be able to hear me now, so you can chat me on the other line, please. I won't be able to receive call on this line. It's being used for the network, so please chat me on the other line. And I think you should be hearing me now. I believe you should be hearing me now. So you can chat me if you are hearing me, please. Chat me now. Let me see your comments. If you are able to hear me right now. Okay. So if you are able to hear me, I am explaining the logic gates. I'm revising what we learned before. This is a representation in terms of switches of the AND gates. AND gate works as two series switches. So until you turn on switch 1 and switch 2, current will not flow through this circuit. Alright. If you turn on switch 1, switch 2 is open, current will not flow through. Or if you turn on switch 2 and switch 1 is open, current will not flow through. Until you turn on switch 1 and switch 2, that is when there will be a flow of current through the circuit that will energize this lamp. So, AND gate behaves in that manner, like two series switches for a two-input AND gate. Alright. So that is how it works. Now I believe you can hear me. Okay, so that's fine. So for the OR gate, I said we can use two parallel switches. Two parallel switches. That is what I explained earlier. Two parallel switches for the OR gate. That's the behavior of the OR gate. Switch S1, switch S2. I said either of these two switches can turn on power to this lamp. If you turn on the switch S1, current will flow through this lamp. If you leave this one open and turn on switch S2, same thing will happen. Current will flow through the lamp. Also, if you turn on the both of them, current will still flow. So that is the behavior of the OR gate. Either or both of the two inputs can give us a high output. But mark you, we can have gates that are more than two, that have more than two inputs. Not necessarily every time the gate must be two inputs. So we have gates that are three inputs, 4 inputs, as the case may be. But basically, that is the behavior of the OR gate. It's just a revision of what we learned before. We also learned about the symbol for these gates. The OR gate has symbol like this. For instance, the two input OR gate. This is the two input OR gate. Inputs A and B. These are logic inputs. And we can say this is Y. And we can represent the function of these gates as Y equals A plus B. The plus here is not mathematical sign, but a logic condition. Logic hard. That is logic or A or B. That's the meaning. For the AND gate, we have the symbol this way. And we can now write inputs A and B. We can now write Boolean expression for the output Y equals AB. Or sometimes you see it in textbook A dot B. It is not mathematical or arithmetic multiplication. It is a logic multiplication, which stands for AND. So A and B. For the NOT gate is an inversion gate, like I said last week. Inversion gate, it always have one input and one output. So if you are sending A into the input, you are going to get A bar at the output. The bar there indicates inversion. That is, the logic state will be inverted at the output. If you are sending a 0, you get a 1 here. If you are sending a 1, you are getting a 0 here. Like you know, we have two states in digital logic circuits, 0 or 1, which actually are voltages. The 0 is about 3 volts or less, and the 1 represents 5 volts in digital circuits. Okay. Now for the NOR gate is an inversion of the OR gate. So NOR gate can be represented like this. If this is OR gate, then NOR gate will be Y bar, which is equal to A plus B all bar. That is it. A plus B all bar. That is inversion. When we are supposed to have a high at the OR gate, we are going to have a low at the NOR gate. Similarly, NAND circuits, the NAND gate is an inversion of AND gate. Y equals AB. So now be bar Y, which is equal to AB bar. Inversion. That is, where you're supposed to have a high, in NAND gate you're going to have a low. So it's interchange. You're supposed to have a low, in NAND gate you're going to have a high. Alright, so that is it. Okay, so that's a revision. XNOR is an interesting gate that behaves in a different way. It does not want the two inputs of the OR gate to be, to be high before it can get an output. So the NOR gate is having this symbol. XNOR rather, the XNOR gate is having this symbol. And it's a selective gate. It's a selective gate that shows that it's only when A or B is either of them is high that we're going to have a high output. We are not going to have a high when both of them are high. That is the function of a NOR gate. It's a selective gate. It selects, it doesn't want the two of them to come in at the same time to bring a high. So it picks only one. If the two of them are high, then in that case we're going to have a low at the output. That's just a revision of the gates that we learned last time. Alright, so I believe you can still hear me. If so, please type the message. Let me see that. Type the message. Can you hear me? Can you see the board? Can you hear me? Type the message into the chat box. Let me see. Okay. I'm waiting for your message to confirm that you can hear me clearly before I move on to the next in this class. That's fine. Miroko Michael says he can hear me. I can see that. Now we want to talk about minimization of logic circuits. Alright, everybody can hear me. So let's talk about minimization of logic circuits. We want to minimize combination of terms when we have several logic circuits working together to achieve a particular logic situation, logic condition. Then we need to minimize the logic combination circuit. Okay? Alright. Why do we need to minimize logic circuits or logic combination circuits? We need to minimize logic circuits for certain reasons. We're going to minimize so that we can have the simplest circuit that we are going to construct practically. If you minimize very well, you get the simplest logic condition that you will implement using the simplest logic gates. That means you are going to have less space needed to implement the circuit. That's one. That means you are going to spend less money to purchase the gates needed. That's number two. Number three, you are going to have that situation. You're going to have a circuit that consumes less power supply, less energy from your power supply. So we have three advantages of minimizing our digital logic circuits. Three advantages. One, it simplifies the circuit such that we have less number of gates to implement. Less number of gates, which will reduce the time of implementation. Apart from that, you will also have less space used on your circuits. Less circuit space. Circuit space is reduced to implement your circuits. And lastly, your circuit consumes less energy. Each logic gate consumes power to operate. So when you simplify your circuit, you have less number of logic gates on your circuit, and that means reduced energy, reduced power consumption. Alright? So we want to look at the laws of logic minimization. We have the idempotent law. Idempotent. Idempotent law. It tells us that A dot A equals A. That is to say, A logic AND with another A will give us output as A. And also, A plus A will give A. That is to say, A or A will give output as A. That is idempotent law. So when you have A dot A in a written linear expression, what you do is to represent the term as ordinary A. Likewise, if you have A plus A, represent the result as ordinary A. So that is that. That is like the idempotent law. We also have the commutative law. Commutative law. Commutative law. Now for commutative law, AB is regarded as BA. That is, A dot B will give us the same thing as B dot A. That is like a multiplication. When you have A multiplied by B, it's the same thing as B multiplied by A. But mark you, this is not arithmetic multiplication. This is logic AND. And the sign between this item, these two terms, is AND logic. Logic AND, the same thing for this. Also, A plus B will give us B plus A. That is to say, A or B is the same thing as B or A in the logic conditions. You understand this better when we begin to simplify combination logic circuits. You understand that better. We have associative laws. Associative law. Alright? Associative law says that AB, into bracket C is the same thing as A into bracket BC. So you can reassociate the terms in this manner. Likewise, A plus B bracket plus C is the same thing as A plus B into bracket B plus C. Mark you, this addition sign is not addition, but rather it is logic OR. Logic OR. So this is associative laws. So you can replace this with this, or this with this. This bracket is not ordinary bracket. It is logic AND. That is what is inside, what the bracket stands for here. AB here has a logic AND in between them, and also between A, B, and C, there's another logic AND. Same thing goes for this. That's a logic AND between B and C, and there's another logic AND between the products of B and C and the logic state A. Are we there? Are we following? All right. So, give the video a like, thumb up, give us thumb up, make comments in the comment section. All right. Now let's look at the next one. We have distributive law. Distributive. Distributive law. Okay. For distributive law, we can have A bracket B plus C equals AB plus AC. Now, in our normal algebra, when you have a situation like this, you say, expand the bracket, open the bracket. A multiplied by B plus A multiplied by C. AB plus AC. So in logic minimization too, we can use this the same way. For mark you, this plus is logic OR. AB has logic AND in between them. AC also has logic AND in between them. Alright, then we have the identity laws. Identity. Identity laws, we have, if you check the notes, we have AF equals F. What does that mean? F here is standing for logic 0. Logic 0. Don't forget, we have two logic states, 0 and 1. So F here is false. False, that is logic 0. So in other words, we can write this one as A dot 0 equals to 0. That is, any logic state that you hand with a logic 0 will give us output as logic 0 from the AND gate. There's nothing you can do about it. Whether A is taking logic high or logic low, once it is handed with logic 0, the result is going to be logic 0. That is meaning of this. AF is equal to F. Also, AT equals to A. That is to say, A dot 1 equals to A. No matter the state that A takes, A can take the state of 0 or 1. No matter what state it takes, it is sent into the same AND gate with logic 1, high. So A dot 1 will be A. Whether A is 1 or A is 0. A dot 1 is equal to A. So whatever happens, if A is 0, then the answer A is going to be 0. 0.1 will be 0. If A is 1, 1.1 will be equal to 1. That 1 is not this one, but A is A that takes that value. Similarly, we also have A plus F equals A. Then we have A plus T equals T. Now remember, F here means false, logic 0. And T here means true, logic 1. Therefore, A plus 0 is equal to A. That is, A OR gate with a logic 0 will always give A, no matter what A is. If A is 0, the final answer here will be 0. If A is 1, the final answer here will be 1. That's what that means. Now, we also have that A plus T is equal to T. That is, A plus true. True means I. So no matter what A is, the answer will always be true. Since there is OR gate in between them. Once we have a high A, no matter what A takes, whether A is 0 or 1, we're going to have a 1 at the output, a true at the output. Then we have the complement laws. Complement. The complement laws, we have this. A complement laws. Complement laws. We have that A handed to A bar equals F. A or A bar equals T. F bar equals T equals F. What do we mean by this? So we need to explain this. Here we have A bar, that is A dot A bar. A and A bar is always false, it's always 0. Because if A is 0, A bar will be 1. If you send the two of them into an AND gate, then the answer is going to be 0. And then if A is 1, A bar will be 0. If you hand a high and a low in the same AND gate, the output will be 0. Here also, A plus A bar is equal to true. No matter what A bar is, no matter what A is, rather, if A is 0, then A bar will be 1. then 0 or 1 will give us a 1, which is true. Or if A is 1, A bar will be 0. So we have 1 or 0, it will always be 1. So that is it. So this one is always 1, this one is always 0. Alright, that's the meaning. That's the meaning of F and T here. Then here, F bar is equal to T. Remember, any logic, any logic input that is having a bar is getting an inversion of the signal at that input. So when we have F and its bar, that means we are going to have a true, the opposite of that, the inversion of the logic of 0. That's what we have here, and the second one also. When you take an inversion of 0, you are going to get a 1. When you take an inversion of 1, you are going to get a 0. Here it's saying 0 bar is equal to 1, and this one is saying 1 bar is equal to 0. This is bar. This is not T, it's bar. This is T, but this is 1 bar. 1 bar. Aha. 1 bar is equal to 0. That is to say, an inversion of a logic state gives, the opposite of that logic state. If you inverted 0, you are going to get a 1. If you inverted 1, you are going to get a 0. So these laws are very, very useful in minimization of our logic circuits. We have De Morgan's law, De Morgan's theorem. De Morgan's theorem. De Morgan's theorem. De Morgan. De Morgan's. Okay. De Morgan's law. So what do we learn in De Morgan? De Morgan's law says that AB or bar equals A bar plus B bar. It also tells us that A plus B or bar equals A bar dot B bar. Also, AB is the same thing as A bar plus B bar all bar. And likewise, A plus B equals A bar, B bar, all bar. Now I will explain this. What is happening is in this situation. De Morgan's theorem is telling us that when you have an inversion of a product, for instance, 2 inputs to an AND gate, when you take an inversion of it, the truth table value for this is the same thing as this. So what happens is that when you have it this way, once you break apart the inversion that you have on the both logic elements, then they are going to break apart, taking their inversion separately, while the sign between them will change from either AND to or gate to AND gate. Like here now, we have AND gate here. AB is a product, that is AND gate situation, and it is inverted. That is a NAND gate now. Now for you to now turn that to OR gate, it means you are going to have A bar separate and B bar separate. This one is what De Morgan states. So here you can say you have demorganized this item to obtain this. You have demorganized this item to get this. Likewise, if you have A or B all bar, that is a NOR gate. You can have a NOR gate, then for you to get it together as AND gate, then you are going to have A bar plus B bar. Alright? Same way, AB equals A bar plus B bar all bar. Now, if you demorganize this, it's going to give you this one bar. If you demorganize, this long bar will break into 2, then it rests into the 2 of them one by one, while the sign changes into hand. So if you now do that, the bar on top of the 2 of them will now be 2, 2. A bar multiplied by A bar, then we have dot B bar. Bar will be, cancelled. When we have double bar, then it becomes positive. You understand? It's inverted now. So bar means the bar will cancel each other. The bar will cancel each other so that we now have AB. Alright? Likewise here, A plus B equals A bar, B bar, everything bar. Now the sign here was initially or, and that sign changes to hand gate. Alright. I hope you are following. Alright. So somebody is asking a question. If you have A bar, star A bar, what will be the outcome? A bar dot A bar. Is that the question? If I get you right, the question says when you have A bar dot A bar, what will be the outcome? So let's look at that. A bar dot A bar. What will be the outcome? Well, if you use the Morgan's theorem, what you have is this. It will be A bar plus B bar, A bar plus A bar, then a long bar will be introduced onto them. That's what you have. Meanwhile, A bar plus A bar is actually A bar. Like we learned in one of the previous laws, A bar plus A bar is actually A bar. Then the long bar comes back on top of it, and this gives us A. A bar is equal to A. So your question, A bar dot A bar will give us A. And if you understand how the logic circuit works, how AND gate works, you will realize that this is what we are going to have. Okay? If A is equal to 0 right now, I'm going to have 1 dot 1. Are you there? If A is equal to 0, A bar will be 1, the second A bar will be 1, then there will be 1 dot 1. 1 dot 1 will be 1. Okay? A bar plus A bar is actually, okay, yes, it's equal to A bar, which is equal to A. So that's what we're going to have. A bar dot A bar. Okay. Like what we have here, here, that's what we have here. But here we have A and B, so we cannot add it together. Like we can add it together here. We have A and B. But the answer is this. A bar dot B bar. So here we should have had A bar plus A bar. And A bar plus A bar will give us A bar plus A bar, then bar on top of them, like this. So the answer is A. Alright? I hope you got that. Okay. So I want to see anyone that has a question again. Does anyone have a question again? Does anyone have a question? All right. Any question there? I want to check if there's any question here. All right. So can you people hear me? If you can hear me right now, let me know. Type yes. Tell me if you can hear me now. Okay, somebody is asking a question. Okay, you can hear me, right? Fine. Somebody is asking a question. What is A bar plus AB? Okay, let's work that on the board together. Let's work it on the board together. A bar plus A, what will it be? Somebody is asking that question. What is A bar plus A? Okay. A bar plus A. What will it be? It's always true. It's one of the laws that we have treated under complement law. A bar plus A. What is it? What's the answer? Now I said A bar plus A is true. So phone for the audio. All right. Can you hear me now? Can you hear me? If you can hear me, please type it. Let's see. All right. So let everybody like the video. I can see 4 likes here. Let everybody like the video. All right. Okay, you can hear me now. So those are the laws of Boolean algebra. We use all these laws in Boolean algebra to simplify the Boolean combination circuit. All right. So we're going to have an example. We're going to simplify some combination of combination logics. We're going to simplify it together so that you can learn how we apply these laws. All right. So we're going to simplify C plus BC bar. C plus BC bar is going to give us something like this. C plus B bar plus C bar. Look at this. We apply Boolean algebra right here. Sorry, we apply De Morgan's theorem from here to get this. This is De Morgan's theorem. De Morgan's theorem. B dot C all bar changes to B bar plus C bar. Now, when we have this, we can now open these brackets and then have something like a C plus C bar plus B bar. C bar and C, they can combine now because of the associative law. But C plus C bar, if you look at a complement law, C plus C bar is always 1. Just like the question that someone asked now, A plus A bar is always 1. So here, C plus C bar, what is here is 1, then plus B bar. Alright? Now, 1 plus B bar is always 1. Because whatever B is, since you already have 1 here, if B is 0, it will be 1 plus 1. Because B bar will be 1 at that point. And if B is 1, then B bar will be 0. Then we have 1 plus 0. The answer is also 1. Mark you, 1 plus 1 in logic state is not 2, it is 1. That 1 means high and low. So 1 plus 1 is always 1 in logic states. I think you get that. Okay. Alright. So that is the first example that we take. The second example is a little bit longer than this. We have an expression like this. AB bar into bracket of A bar plus B. A bar plus B bracket B bar plus B. This is what we are given. We want to simplify this. This must have been the output of a particular combination circuit, logic combination circuit, when we have so many gates together. So we want to simplify what we get there. Reason being that we need to get the simplest form of the logic gates to implement in order to save costs. Okay? We want to save costs, we want to save a circuit space, we want to save power that we need on the circuit. So we need to simplify. So if this was an output from a combinational logic circuit, then one should not go ahead and go and implement it this way. Go and buy so many gates to implement. No. You simplify it to the least, then you implement. Alright, for instance, the first example we took here, we simplified this and we got high. It means wherever all this expression is required in the circuit, all these gates is required, the engineer will just neglect all of them and use a high, which is 1. And what is a high? 5 volts. The engineer will just connect 5 volts to determine where this particular expression is required, because it's equivalent to 1, which is high. So 5 volts will be connected to that terminal and it will work perfectly. You can now see that it saves times, save cost, save energy, save everything if you can minimize the combinational logic output. So let's look at this. Let's look at this. We are going to have something like this. AB bar into A bar plus B. Why? B bar plus B is always what? 1. So we are going to have A bar plus B multiplied by 1. And it's going to give us this back. That's it. B bar plus B is always 1. Just like the question we treated, A plus A bar is always 1. Take note, it doesn't equal to A but to 1. Alright, that is the complement law and identity law. That's what we can derive from that. Now we need to demorganize this particular A, B, or bar to give us something similar to this. So we are going to have A bar plus B bar into A bar plus B. Alright, into A bar plus B. And that's, if you simplify that, you will realize that A bar will be retained. If you simplify it, A bar will be retained, and then B bar dot B will be retained. But A bar dot A bar will be A bar. That's what will remain. And then B bar dot B bar will also remain. A bar dot B bar, they will be removed, because distributive law states that. So the output of this is going to be A bar plus B bar B. That's the output. Now when you have this also, B dot B bar is also an identity that we should quickly realize. B dot B bar is always 0. B plus B bar is always 1. B dot B bar is always 0, because B, an inversion of B, in the same AND gate will give a low output. It's always 0. So the answer to this circuit is A bar. So with everything that we have very long here, we arrived at a small expression, which is actually just an input to represent the whole of this, which is a single input, probably with a NOT gate. So we can use a NOT gate to achieve this. So just have a NOT gate this way and connect terminal A to it. So this is what we need. Outside here we get A bar. It is that A bar that will represent everything here, and it will work perfectly. Now assuming the engineer that did the combination circuit is going to implement this, then we need, let's see how many gates we need to implement it from here. We need one NAND gate here, A, B bar. That's one NAND gate. We need NOT gate to get A bar. We need another NOT gate to get B bar, making three gates. We need one OR gate between A bar and B. That is A bar or B. Then we need another OR gate here, B bar plus B. So making 5 gates. Then we need one 3 inputs AND gate that will now feed this as one input, this as another input, and this as another input to that. So we are going to have 6 gates to implement this from the raw, the way it comes from the combinational circuits. So we cannot implement it that way. We need to simplify it, and the simplification shows that the entire of this can be represented as A bar. Isn't that very interesting? Isn't that very sensible? And that is what engineers do when they finish, a combination circuit. They, walk through it, bring out the final expression at the output, and then simplify it. After simplification, then we get the simplest form that should be implemented. That saves cost, saves energy, saves, circuit space. So that is it. All right. We are moving on to the next example. We are going to simplify. In this case, we are going to have A, C, and D in the inputs, and the inputs of the combination circuits. A, C, and D. All right. So today, the simplification is what we are dealing with. Simplification of logic gates. All right. So we are told to simplify. We are told to simplify an expression that is a bit longer than what we did before. Okay, we have A plus C, AD plus AD bar plus AC plus C. Yeah, this is very interesting. It's long. So what do we have? To simplify this, C, no, into A, because from here we can bring out this A, like a arithmetic factorization, A is coming out of this bracket to leave D plus D bar. This is a Boolean algebra, and that is a distributive law. We are trying to apply distributive law here. And also we now have C. We can bring out C also. C into A plus 1. A plus 1 is always 1. So 1 dot C will give us C in the next line. Okay? So we have A into A plus C. That is, we factorize this A out now. We now have A plus C here. A plus C. Okay? Multiply by here, D plus D bar. D plus D bar is always 1. So this one remains 1. So there's nothing left here. So A remains here with D. So we factorize it out. Then we can go ahead and close that. And then we write plus C. No, plus C. Because A plus 1 is 1. 1 dot C is C. So our final answer can be, we can write this as AA plus AC plus C. Okay? And then when you have this, this is C can be factorized out. A dot A is A, and C can be factorized out. C into A plus 1. So A plus 1 is actually 1 dot C, and the final answer will be A plus C. A plus C. Alright, if you check the notes, this one is represented as T, true. It's represented as true. It's represented as true. So what we have there is a very simple expression to represent all these. Just one OR gate, 2 input OR gates, and the inputs that we are going to take into that will be A and C into the OR gate. So that is it. Simplification of the logic gates. Now let's take one more before. Okay, the last simplification that I want to do now is one long expression also. One long expression that we want to simplify to see the simplest form of it. At this point, I don't know whether you have any question. You can type your question and let me see. Type your question, let me see if anybody has any question. Okay. All right. So if you have any question, let me see before I go to the last one. Does anybody have a question here? Okay, I can see that you are finding it interesting. You are finding it interesting. So let's look at the last one. We are to simplify a bar into a plus b plus b plus aa into a plus b bar. Okay, that's the expression given. Alright, to simplify this, we apply the Boolean algebra step by step with De Morgan's theorem. Now we can open up this kind of a distributive law. A bar A plus A bar B, right? Plus here we can have okay, there's a mistake here. The bracket is A and then plus B plus A, B plus AA. Okay, it is still B plus AA, B plus AA, bracket A plus B bar. Yes, it's correct. So this AA, A dot A is actually A. So we're going to have B plus A there. B plus A. Now we're going to have B plus A into B bar. Okay? Plus B plus A into B bar. Into B bar. Alright, so we use the distributive law 2 times. Now having that, we can go ahead and represent this one. A dot A bar is equal to 0 always. So we now have A bar B. That is this. This one has gone to 0. A dot A bar every time is 0. So we now have A bar B plus B plus A into A. B plus A into A. Okay. There's something missing here. B plus A into A. B plus A into A plus B plus A again. B plus A into B bar. B plus A multiplied by B bar. Okay. So B plus A into A plus B plus A into B bar plus B plus A into B bar. B bar. Now the way it is now, we can see that we have common terms in these brackets. So it can help us with B plus A into A. We can open up this to simplify something. A bar plus AB plus A, that is A dot A will be A dot A will be A. Then plus B dot B bar. B dot B bar will be 0 at the end of the day. Then plus A B bar. B dot B bar will be 0, A B bar. So this one will go to 0. The next line, we will not see that one again. Then this one will remain 1. 1 plus this will be this. So we're going to have A bar B plus AB okay, BA plus AA, sorry, that is A dot A here. A dot A, which is actually A. It's always A. So here we can now do the factorization. We can do a factorization. This one goes to 0, then this remains this and this remains plus A dot A plus A dot B bar. This one goes to 0, then A is common in here now. So we can say A bar plus A into B plus 1 plus B bar. So this one, B plus 1 plus B bar will be B plus B bar. And B plus B bar is always 1. B plus B bar is always 1. So finally, we have A bar B plus A. All of this is 1. 1 plus 1 is 1. So now we can simplify this further as A plus A bar. That is using distributive law again. A plus A bar, then plus in brackets A plus B. Now A plus A bar simply will give us A plus A bar is always 1. So final answer will now be A plus B, because A plus A bar is 1. So 1 times A plus B will now be A plus B. The final answer is A plus B. So it's very interesting, but requires a lot of application of identity laws. Identity laws like commutative, distributive, associative, identity. Sometimes De Morgan's theorem is applied to achieve the simplification. Now you go ahead and check questions, the past questions, to practice simplification of logic circuits using Boolean algebra like this. Now later on, we are going to also learn simplification of logic circuits using Karnaugh map, K-map. So in our next video, we're going to learn that. So I encourage you to please like and share the video, make comments. If you are a new subscriber, you are so much welcome. Subscribe to the channel. We are going to give more educative information on electronics, computer, instrumentation, computer hardware, computer software, and even mathematics. So until next video, bye. Now for those that join live, I don't know whether you have any question. Is there any question here? Is there any question? Please like the video and type your question down before we end the live session. Before we end this live session, I want you to please type your question so that I can respond right now. All right? Yeah, I know it's very interesting. So like this last one, look at the long expression that is output of a particular combination circuit. The simplification is A plus B, and that is a single OR gate, 2 inputs OR gates with inputs A and B sufficient to implement the whole of that. So it's very, very interesting, and you must not, as an engineer, after determining your combination logic, you must not go ahead immediately and implement. You must first of all simplify in order to save time, to save costs of implementation, to save circuit space, to even save the power that you are going to supply to the circuits. You will need more power. The more components you have, the more power you need to supply to the circuits. The logic gates, they take power in order to be energized and operate. So that is it. So simplification is very, very important. So bear that in mind. So let me see your question now so that I can respond before we end the live session. So somebody is asking question. So if you explain the second line of this last example. The second line of this last example, okay, so what you need to do here, I do not expect you to grab everything right there immediately. You need to go and learn more about commutative law and associative law. It's very important. That is what is happening here. We have distributed something twice out of here to get here. So distribution gives us this, produce this from here. Okay? But when you study those identity laws that I gave, you now see that it is true. We are going to achieve this. But from here, you now see that it's become familiar because it's more. It looks more like arithmetic like normal algebra. It is not algebra anyway. The signs here, they are not addition and multiplication, but rather logic states or and then and. And take notes, we have bar. Those bar, they are not division. They are, inversion of a logic state. I think you get that. So I saw another question there. It says, I need the breakdown of the second to the last expression. Second to the last expression, if it is this one you mean, AB, that is where the law comes in again. We have distributed A bar B plus A. How did we arrive at this? It's a law that we employ. It's a simple law that shows us that this and this, they are the same. But if you want to actually find out, you can try to expand this. If you expand this carefully, you arrive back at this. And that is what the law states. Here now, A multiplied by A, that will be A dot A. Then A multiplied by B, A dot B. Then we'll have A bar multiplied by A bar dot A. Then A bar multiplied by B. Now, the law tells us that the terms in between will vanish. It will now remain this dot this, which is this, and this dot this, which is this. But the ones in between, the expansion in between will vanish by logic, minimization. But if you want to truly confirm this, you need to, use truth table to do that. You will put all these things in truth table. You now see what we did the result of A bar B plus A for a 2-input, gate. When you finish, you go ahead also and implement this. Mark you, to implement this, you will need 3 gates. You have one hot gate here, and 2 input AND gates that will take this one and this as inputs. Alright? So when you simplify, you're going to arrive at the same truth table as this. That is where the situation requires you to master the logic minimization laws. It's not going to happen by magic. You need to familiar yourself with those. If you check the laws, one of the laws states that, and it's very interesting. That law used to be very, very interesting when you are simplifying logic states. And that is it. The distributive laws. That is what we used from here to here. So for now, I want to say in the next class we move on to more example, which will be in form of a table. Then we have so many states to reach, and that is it. So for now, we are going to end the live session until another time. Do like and share the video. If you have not subscribed, please do so. Make your comments so that we can respond as well.
Bye for now.
All right. So we say bye-bye until another time.